Hello again everyone, welcome back to ptet.chemistry channel. So as you have known, there was a recent copyright issue with all the exam papers that I was showing. So going forward, I've decided that we will just be doing paper tutorials such as these. This is a March 2021 paper for the 9701 Cambridge International A-Levels. This is I'm going to do a paper 1. So this is a paper 1 component 1 variant 2, so there's only one variant for the March 2021 paper. And so going forward I won't be showing the question papers, but hopefully you will find that the way I explain through the questions are nothing different from how it was when I had a question paper in front of me. Right? I do believe that you will be able to source your own question paper, assuming that you're at a Cambridge school, and however I cannot tell you how to find them, so that's up to you. Alright, so without further ado, let me get started. In this first question, so we're given a table with 4 species, W, X, Y, and Z, and we have number of protons, number of neutrons, and number of electrons. We are asked about isotopes. The question is basically which pair represents the atoms of 2 isotopes. So there are a couple of key terms here. So one of which is isotopes. So when you read through this MCQ, you should really underline or circle or remark on what is important about this kind of MCQ. So they first started out by saying atoms. So when you have atoms, that is uncharged. And if atoms are uncharged, then the number of protons equal to the number of not neutrons, but electrons, because the charged species have to balance each other out such that atom overall has 0 net charge. Now the second bit is about isotopes. So isotopes have different number of neutrons, but same number of protons. So do you really need to write all this down? You probably don't have to, because these are things that are running through your mind as you read through the question, if you know your theory. So based on that information, in fact based on this first information, you can cross out option X. So in the box given, you can cross out option X. This is wrong because you have 32 protons and 34 electrons based on the option. And you can cross out, so X is out, and then they say atoms of the same element. So there's the next thing, which is same element. So same element means the identity must be the same. So it's the same number of protons, which is basically the point that I've mentioned up here. All right. So same number of protons. You can see that WXY has 32 protons. So you can cross out Z because Z has 34 protons. So after we cross out Z and X, we are left with pretty much only one answer, which is option A, that is W and Y. Question 2, what do we have in question 2? Where in the periodic table is the element that has an outer electron shell arrangement? So they told you that you're looking for something which is 4s2, 4p3. They tell you it's the outer shell arrangement. So outermost shell is to do with valence shell. This is a 4s2 and 4p3. The 4s2 is completely filled. The 4p3 is not completely filled. If you think about the p block, this is a p subshells where they have 3 of these orbitals, px, py, and pz. They have the same energy, but then in your periodic table, going from group 3, p3, group 13, 14, 15, 16, 17, and 18. So there's P1, P2, P3, P4, P5, and P6. So you can fit 6 electron maximum in the 3 p orbitals for the p subshells. So we have this thing called 4 and 4. So what that tells you is it's in period 4. So it's in the 4th shell, and then altogether we can imagine that it has got it's got 4p3, but altogether what it has is 2 and 3, so total of 5 valence electrons. Okay, valence electrons, because in your valence shell n equal to 4 you have 2 plus 3 valence electrons, so 5 valence electrons. So we're looking at group 15, which is P3. So group 15 period 4, they will give you option D pretty much straight away. Question 3. So substance Q is hydrocarbon. So hydrocarbon I can express as CXHY, a compound containing carbon and hydrogen only. That's the definition of hydrocarbon back from O-level or IGCSE chemistry. You're given the information that 1 gram of Q completely burns, so this complete combustion. So completely burn means complete combustion, that is in excess oxygen. And they will give you CO2, and they don't tell you the other products, but the mass of CO2 is 3.22 gram. So you're given 4 options. The first option is cyclohexene, which is C6H10. So cyclohexene is a 6-membered ring with 1 double bond, so it's just 6 carbon. There's 2 hydrogen, 2 hydrogen, 2 hydrogen, 1 and 1 hydrogen, because carbon form 4 bonds. These are skeletal formula. In fact, this is how the structural formula of a cycloalkane or cycloalkene looks like. We just draw using the skeletal form. So C6H10 there. B is cyclopentane. So cyclopentane is a 5-membered ring, and it has got no double bond, so there's just C5H10. Is that correct? Yeah, there's C5H10. This was C6H10 and not C6H12 because there's a double bond there. Option C is to do with ethene. Ethene is C2H4. So, well, I can draw the display, I guess, because it's nice and easy to show you. So C2H4 like that, where the carbon form 4 covalent bond and the hydrogen form single covalent bond. For D is pentane. Pentane is C5H12. If I just draw the skeletal formula, CH3, CH2, 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 CH3, because carbon form 4 bond, carbon has 3 hydrogen here because you show only the bond bonded to carbon. Carbon form 4 bond, 1, 2, so there are 2 carbon hydrogen bond, 2 carbon hydrogen bonds, 2 carbon hydrogen bonds, and 3 carbon hydrogen bond there. Anyway, given the formula of each of these, I don't really know at this stage whether I need to calculate the MR or not, but let's think about what we can do here. So I hope you can imagine that if you have CXHY plus O2, there is an equation for this. You can have a look at one of my A-level concept videos. So they are no longer topical playlists because I had to take those down as well. But the A-level concept videos outline some of these combustion of gases problems, which I show you how to get to this equation. But anyway, I'll show you how to get it regardless because it's quite an important one. So CXHY completely burn in oxygen to give you carbon dioxide and water. So X number of carbon, assuming there is 1 here, X number of carbon, it will give you X CO2 because this is the only substance with carbon. There's Y hydrogen atoms here, but this is H2, but altogether I need a Y number of hydrogen atoms. So what I do is Y over 2, because Y over 2 times 2 is your algebra. It will give you Y number of hydrogen atoms. Altogether now on your right hand side, you have 2x for the oxygen, and then you have Y over 2 times 1. So this is the number of oxygen atoms, this number of oxygen atoms. But again, this is O2, so what you do is you have half of 2x plus y over 2. That will give you x plus y over 4. This is just your classic expansion of algebraic terms, such that you get this generic expression for the complete combustion of a hydrocarbon in excess oxygen to give you carbon dioxide and water. Alright, so based on this, what we can say is the mole of the hydrocarbon is to the mole of CO2 is 1 mole will give you x mole of CO2. I suppose I can write it here. So what does this all tell us? The mole of CXHY is to the mole of CO2 is 1 over x. This is from the balance equation. 1 mole give you x mole of it. And this thing on the right hand side will be I burn 1.00 gram and this is the MR of the CXHY, which is our unknown compound, which is our hydrocarbon Q. So Q is the hydrocarbon. So what I could do is I could write MR of Q as well if I want to. Perhaps that's what I should do. So MR of Q. And then at the bottom there is the mole of CO2. So I produce 3.22 gram of CO2. So that's divided by 44. So if you run up the math, and then that should give you what I want is I want X as the subject. I want X as the subject. So X is equal to 3.22 over 44. Hang on, not yet finished. So I invert it. So 3.22 over 44 divided by that. So that is times the MR of Q over 1.00. So 1.00 is just 1. I just need to find the MR of Q. I have all these molecular formula, so I can find the MR of Q. So the MR is going to be 12.0 times 6 plus 10 times 1.0. On your calculator, you get 82.0. This is going to be 5 carbons, so 5 times 12.0 plus 10 times 1.0. I got 70.0. On the other side, I get 28.0. You can do the calculation yourself if you can get the correct molecular formula. So with all these molecular formula, what I could do is I could use this expression, which is finding out what is this value X here. So we need X as the number of carbon atoms. All right. So based on that formula, which you have gotten from there, if I just draw a box so that we can emphasize on the importance of it. So what does that give us at X? You can put in the value of 82.0 into this equation. You get X equal to 6.0009. You get X equal to 5.123. You get X equal to 2.049. Bear in mind that I have actually done this paper tutorial previously with the question paper in front of me, so I do actually have the solution somewhere, which I cannot share obviously, which is why I'm doing this calculation a lot faster than in those tutorials where you will heard me clicking on the calculators. Alright, so perhaps in the future tutorials on the papers which I never done before, it would definitely take me a while to press on my calculator to actually do this from scratch. So this gave me 5.269. I'm basically looking at my previous responses. But yeah, I mean, the idea is that I have to restart the channel from scratch, which is why you don't see a lot of tutorial videos in the meantime. Anyway, looking at what X was supposed to be. X was supposed to be the number of carbon atoms in the formula of Q hydrocarbon. If you have C6H10, this is 6.0009. This is the closest value to 6. This is 5.1, it's not as close to 5 compared to this with 6. This is 2.049, again not as close as this to 6. This is 5.2, quite far off from 5 compared to this, and also 6. This is the closest to the actual whole number, and the correct answer there must be A. Question 4. So question 4 is a tricky one as well. I remember that in my old tutorial videos before the marking scheme was actually released, a lot of students keep on telling me, like their data booklet showed them the AR or indium to be 154. So surely the answer must be D instead of B. But they say using this data. So if you see the question, they say use this data, it means use this data. Okay. So they say indium oxide was originally thought to have this formula. So it was originally thought to be indium oxide. So they show that indium, In, and oxygen, so 4.8 gram of indium combined with 1.0 gram of oxygen to give you indium oxide, which is 5.8 gram. So this is what they thought, the ratio. So they thought the empirical formula, which is the simplest ratio of the atom, is indium 1, oxygen 1. So since that is the mass, and then I can work out the AR of oxygen, which is 16. That was what is given in the question, not from a periodic table. And then I let this one be Y, which is the relative atomic mass of indium that I'm supposed to find based on this data. So my mole is going to be my mass over the relative atomic mass for the atom. So 4.8y and then 1.0 over 16. And remember that we want the simplest ratio. So the mole of indium over the mole of oxygen is 1 over 1. And how do I get mole is 1 over 1? Because of this thing here. These are from the information given that the formula is 1 mole of indium to 1 mole of oxygen. Then I do on the right hand side my actual data. You have seen this from all my mole calculations video that I like to express my mole ratio like this as my bookkeeping label from the balance equation and then the actual data. So the actual data there refers to mole of indium on top. This is the mole of indium because I've chosen to label indium on top. If I've gotten the other way around, I will have this the other way around because it follows the bookkeeping. What did you label? All right. So if I move this up and make y the subject, so 4.8 over y equal to 1.0 over 16. Since this is just 1 over 1, which is 1, I can move the y up there, I move the 16 up there, and I move the 1.0 down there. So 4.8 times 16 over 1.0. Press that into your calculator and you get y is equal to, well, you get a value, first of all, onto your calculator. You get 76.8. And that's rounded up to 77. That's the nearest whole number, as the option given is not to any decimal place at all. And remember what y was? Y was relative atomic mass, as we label it, is for indium. Okay, and that's what the question is asking. So this has to be option B. Okay. Moving on to the next question, question 5. So one of the key terms you can underline or circle is this term called only intermolecular forces, and you want it to be temporary dipoles. So temporary dipoles refers to induced dipoles. So we are looking at van der Waals. Looking at the options given, hopefully you can see hydrogen chloride. This is not hydrochloric acid because this is a pure substance. Hydrochloric acid is a mixture of hydrogen chloride dissolved in water. HCl aqueous is a mixture. Okay, so this one has a permanent dipole as a result of chlorine being a far more electronegative element. So what you have there is you have permanent dipole. Actually, I think of a better way of doing this. I should really set up a kind of imaginary table, van der Waals, permanent dipole, as a result the molecules being polar, as well as hydrogen bonds. So you definitely have van der Waals because you have electrons in molecules, you have permanent dipoles, but you don't have hydrogen bond because you don't have hydrogen bonded to fluorine, oxygen, or nitrogen. Moving on to the next one, I have methanol, so CH3OH like this. I definitely have delta negative, delta plus, and don't forget that you have hydrogen bonded to oxygen. The electronegative element also have lone pairs on them, so you could have hydrogen bond. This molecule is polar because anything that has hydrogen bond definitely is a very polar molecule. You also have van der Waals. Definitely not the answer there because you do not only have van der Waals. Okay. The other option would be octane. Octane is C8H18. This is a hydrocarbon. A hydrocarbon is considered non-polar, even though there's a slight difference in electronegativity between carbon and hydrogen. These are usually negligible and we can call them non-polar. Definitely they do not have hydrogen bonds, and we are looking at option C as the only one that has only van der Waals. And of course the last one, you're looking at water. Water definitely has hydrogen bond. That explains the very high boiling point of water, even though it is a simple molecular structure. So hopefully that makes sense to you there. Question 6, what do we have? We have 0.25 gram of sulfur dioxide, SO2, in 1.00 dm cube of H2O. So we are talking about sulfur dioxide solution, but they say that the SO2 gas goes to SO2 aqueous in water. So by right, it's actually H2SO3, but that's what they say, the SO2 dissolve in water, which they have 0.25 gram of it dissolved in the water. But we are talking about the gas, so we're talking about these, and we have to use this thing called ideal gas equation, where we assume ideality. They say what volume of sulfur dioxide, because that's referring to gas, since the question also mentioned pressure. If I start by writing my ideal gas equation, PV equal to nRT, PV equal to mass over mRT. One of the most common mistake that a lot of students make is they try to put in the value at the very beginning, and they are just rewriting the value again and again while rearranging equations, and that often lead to far more mistakes and waste a lot of time. I would say that always find out the subject. You want the volume of gas here, so it's mRT over P times mR. Just like that, on the side, think about each of these. This belongs to the mass of gas in gram, molar gas constant, temperature of the gas in Kelvin, pressure of the gas in Pascal or Newton per meter square, mR of the gas in gram per mole. So look at the data on the side. I have mass of the gas that dissolve in that much water is 0.25 gram of the gas that dissolve in it. Mass doesn't change. This much mass goes into the solution. So this is the mass of the gas. The next thing, R is straight from your data booklet, 8.31 joule per Kelvin per mole. It has units. And then temperature was, it is given in degrees Celsius. So converting 50 degrees Celsius to Kelvin is plus 273 Kelvin. That gave me 323 Kelvin. What else? Number 4, this is to do with pressure. So pressure has already been given in Pascal, so we are nice and happy there. And then number 5, the mR of SO2 gas is 32.0 times 1 plus 16.0 times 2. I get 64 on my calculator. By right, I know what is appropriate number of significant figure. It doesn't matter. Oops, I have done one mistake. It should be 32.1 based on the A-level periodic table. I think I've taught O-level reasonably long enough that I am slowly shifting towards the O-level periodic table now. Anyway, so this is gram per mole. So what you could do now is, based on all of these, you know these in the correct units, sub it into your calculator, and you can get volume is equal to 1.047 times 10 to the power minus 4 meter cube. We then have a problem. The volume is in meter cube. The option is all given in cm cube. This question is really tedious actually. Anyway, so we have to think about conversion. So converting meter cube and cm cube, I would start by 1 meter is 100 cm, so 1 meter is equal to 10 square cm. If I cube both sides, okay, so I never remember these kind of things. I rather work it out from scratch because my brain is quite valuable to remember so many things. Equal me whatever you do on the left, you do on the right. So 1 cube is 1, meter cube is meter cube. 10 square cubit is 10 to the 6 cm cube. Now I want to convert meter cube to cm cube, so volume is equal to 1.047 times 10 to the power minus 4 times 10 to the 6 cm cube. Therefore, the volume is, what do I get? So 10 to the 6 and 10 to the minus 4 give me 100, which is 10 square, so that give me 104.7 cm cube, and the closest answer is 105 cm cube. This is option D. Question 7, what do we have? We have a calorimetry experiment. So calorimetry is to do with heat transfer and stuff like that. In the setup given, you're given the mass of water. So all these are algebra terms, doesn't matter. What you could do is you could start off by Q of the solution, because the heat energy transferred to the solution, which is mostly water, which we assume is all just water, so it's of the water. Your mass of water is W gram, multiplied by the heat capacity of water, which is 4.2 joule per Kelvin per gram. And I want the delta T, temperature rise. They said the delta T is TF minus TI. You are given in the question temperature rise is equal to y degrees Celsius. This is your delta T in that. But as you know, when you have temperature scale, if I have a scale in degrees Celsius and also in Kelvin, I should really use a different color so that I could see the big difference. If I have 0 degrees Celsius, then what I have is 273 Kelvin. So if I have, I don't know, 25 degrees Celsius, what I have is 273 plus 25, which is 298 Kelvin. So hopefully you can see that, you know, when you have difference, the delta T in Kelvin is exactly the same as delta T in degrees Celsius. So the difference in temperature is always going to be the same whether you're in Kelvin or degrees Celsius. This is in Kelvin because this is temperature rise, but this is given in degrees Celsius, but this is temperature difference, temperature rise. They are going to be the same based on this very simple diagram just shown you. So the delta T there in degrees Celsius, I can show it as Y Kelvin because the change in temperature in degrees Celsius is the same as the change in temperature in Kelvin. So hopefully now you can see the per Kelvin and Kelvin cancel, the gram and the gram cancel, gram and per gram cancel. You get 4.2 W times Y. This is given in joule. So what about the second one? I have the molar mass of ethanol and the mass of ethanol burned. So the mole of ethanol is going to be the mass over the MR of ethanol. The mass of ethanol burned is given as X gram, that's the correct unit. And the MR of ethanol is given as Z gram per mole. That will give me X over Z mole. Now, this is in joule. They want your answer in kilojoule per mole. So if you read the question very carefully, they did say in kilojoule per mole. All right. We also saw that delta T was temperature rise. This is of the solution. So your solution gets warmer because the reaction releases heat. So we are talking about combustion. So combustion is always exothermic, and that is why this reaction releases heat. That's why the outside, which is the surrounding, increases in temperature. So we are expecting an exothermic reaction. And an exothermic reaction, you must have a negative sign. You must reverse the sign of these with a negative. So that's why anything with a positive is not going to cut it. What else can I say? You're given the option A, B, C, D. Because of this thing I just said earlier, you can cross out option D. So cross out option D, which is wrong already. You're left with A, B, and C. How do you decide what is correct? You follow the units. The delta H combustion is going to be the enthalpy of the solution, which is part 1, but don't forget that the solution is the surrounding. So I need to reverse the sign for the system releases heat energy, and then I divide by the mole of the limiting reactants, the stuff that burn, which is the ethanol. I'm going to combine everything together. They want it in kilojoule per mole. I have this in joule, so I need to do this divided by 1000. 4.2 WY, 4.2 WY divided by 1000. So that will convert this to kilojoule. Don't forget the minus. And then I put in the X over Z as the mole of ethanol. So X over Z as the mole of ethanol. How do I say this? Yeah. Let's see. This one minus divided by X over Z. So what will that give me? That will give me minus 4.2 W y z over 1000x. Alright, which means the correct option will be option A there. So a lot of algebra terms really scare a lot of students, but you know, if you're given the actual value, you're doing the exact same thing. If you know the method, you will not be tricked. Moving on to the next question, question 8. So you have you're given the VO2Cl, and you what you have is some other stuff, and you get VOCl2 plus VOSO4. They said that the oxidation state of chlorine there is -1. If there's -1 for this compound, This compound doesn't have any charge, so 0 is equal to vanadium, which you want to find the oxidation state. 2 times minus 2, because minus 2 is the oxidation state for oxygen, the compound. You have 2 of it. And I have 1 chlorine. Each of it is minus 1. So vanadium there is going to be minus 4, minus 1, move to the other side is going to give me vanadium plus 5. In VOCO2, the compound again is uncharged, so the overall oxidation state is 0. Vanadium plus 1 times minus 2 plus 2 times minus 1. Vanadium there is going to be vanadium plus 4. And last but not least, VOSO4, so 0 is equal to vanadium plus minus 2 times 1 plus, I don't know the sulfur. Oh, actually I do know the sulfur, because this thing here is SO4 2 minus, and you have this one of it. So, you know, I could have gotten away with VO2 plus SO4 2 minus like this. So I suppose this will be plus 2 equal to vanadium plus minus 2. Vanadium there is plus 4. I don't think they are expecting us to use that at all. So what can we do? We look at the vanadium. So the plus 5 going to plus 4 is I don't like that arrow at all. Plus 5 going to plus 4 is a reduction, because your oxidation number or oxidation state decreases. So you're looking at option C and D, so not A, not B. And then obviously you look at the iodide. So you have NaI going to I2. This is I minus 1, because this is what you call iodide. You can either try working from scratch, or you can just know it from the name. Sodium iodide, Na plus, I minus. So it's I minus 1. This is iodine as a molecule. This is increase in oxidation number. And if you increase the oxidation number or oxidation state, that's what you call oxidation. So the iodine does get oxidized from minus 1 to 0 in that product. So altogether, that gives you only option C as the correct answer. Question 9, what do we have in question 9? We want water as a Bronsted-Lowry base. So if you think about Bronsted-Lowry, is to do with proton acceptor or proton donor, but this is a base, so we're looking at proton acceptor. If you think about water is H2O, oxygen from 2 covalent bonds like that, and it still has 2 lone pair, giving you a 2 bond pair and 2 lone pair. The bond pair repel less than the bond pair lone pair, repel less than the lone pair. That's going to give you a band geometry with a bond angle of 104 or 104.5 degree. That is not what the question is asking you. So what do we have? I wonder if I can move this down there, because I feel like we need quite a lot of space to discuss the next bit. I believe I can, so as easy as that on the screen. Not as easy if you're working on paper, obviously. So what we have is option A. Option A, you have H2O plus sodium going to NaOH plus H2. Hydrogen there is plus 1, oxygen there is minus 2. Sodium is 0 because the oxidation state of an element is going to be 0. Okay, so Na is plus 1 because this is Na plus 1, OH minus 1. This is hydrogen 0. So this is very clearly a redox reaction. A redox reaction is not an acid-base reaction. Okay, so you can see that the water has been involved in going to hydrogen. So this is not a simple acid-base reaction. I can cross out A. B involve H2O plus H3PO4, giving you H3O plus H2PO4 minus. You can hopefully see here that the water has used the lone pair. It has used one of the 2 lone pairs to take up the H3O plus. It's got 2 lone pairs. Now when you use one of it, OH and OH, and then you use one of it to form a dative covalent bond, you still have 1 lone pair, but now you have a positive charge. and now your bond angle is no longer 104.5, it's now 107 degree, because now you have three bond pair and one lone pair, just like ammonia, because this is now no longer a lone pair, it is a bond pair, a covalent bond. So here the water acts as a proton acceptor. It accepts a H plus and give you H3O plus. Therefore, it's acting as a base, and this is your correct answer. Then why can't we accept option C? Why can't we accept option D? In the real exam, when you already got to the correct answer, you will move on. But for the sake of learning, you gotta know that the next time you face with this kind of scenario, you gotta know why they are not what you're looking for. Alright, so this is not an acid, this is not acting as a Bronsted-Lowry base, because the H2O there, what actually happens is you can think about this, this is a basic oxide. When you dissolve in water, you're gonna get alkali. So that has not really accept a protons. This is OH minus. So going from here to here, the H2O loses the H plus, not a proton acceptor as required by Bronsted-Lowry base. Now you have NH3 plus the CuH2O6, 2 plus, and you get NH4 plus blah 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 blah. Actually, I should probably write out the blah 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 blah, because that is the important bit there. This is part of A2 transition metal chemistry actually. So after you lose, after one of the water loses the H plus, so one of the water, so one of 6 H2O molecule, what we say is it gets hydrolyzed, loses the H plus. Okay, so the H2O loses the H plus, it is not acting as a H plus acceptor, it loses the H plus, you're left with 5 water and a hydroxide. Instead, this gain the H plus, this is the H plus acceptor, this is the base here, and this is the acid here. Alright, so that's why the correct option there has to be option B. The correct option is option B there. Question 10, phew, a quarter of the way through. So we have a large excess of marble chip. So you have excess. Marble chip is basically calcium carbonate. So calcium carbonate is a metal carbonate. You react with, what do we have? We have 25 cm cube, 1.0 molar HCl. This is at 40 degrees Celsius. So quite a lot of factors that can affect rate of reaction. Temperature, of course, is one. The concentration of the acid, of course, is one, and this is to do with marble chip. So you can have powdered form, which is a larger surface area, compared to the lumpy form, which is smaller surface area. They ask you, how would it be different? How different? If you have 60 cm cube but 0.5 molar HCl, and you still have 40 degrees Celsius. So same temperature. So we are not concerned about temperature at all. And I am assuming that we are still using steel excess marble chip, because they didn't tell us otherwise. So if we are still using excess marble chip, therefore HCl is limiting. HCl is limiting means however much gas or however much product you get come from the mole of HCl. The mole of HCl here will tell you how much product you will get. The mole of HCl here will tell you how much product you will get, because your product comes from reactants that reacted fully and not the excess as stated in the question. Alright, so the first thing I would do is I will work out before the mole of HCl used is going to be 25 times 10 to the minus 3. To convert this cm cube to dm cube, times 10 to the minus 3 mean divide by 1000. So times 1.0 mole per dm cube, and that give me 0.025 mole. Now on to the next one, the second example. So in the new reaction, actually I should probably not use before and after. I should really use reaction 1 and then reaction 2 to indicate that it's a different reaction. But I have used a different volume, so 60 times 10 to the minus 3 to convert it to dm cube, sorry, multiplied by the concentration in mole per dm cube. This is dm cube, by the way. So dm cube and mole per dm cube, dm cube and mole per dm cube. This give me 0. Oops, I don't want that. This give me 0.03 mole. So as you could see that here in the second reaction, you have more what? More HCl, which is limiting. So if you have more of the limiting reactant, therefore we get more products. That's number one. Okay, more products. If you have more products, that means you can cross out not B, not D. Okay, not B and D, so you're left with A or C. But then you have a look at the concentration. So concentration wise, this is this and this. More concentrated will be faster. More concentrated HCl is faster reaction. So this is to do with rate of reaction, faster reaction. Okay, so the reaction will be slower because this is less concentrated than this, but you will get more products out because you have greater mole of the acid. In terms of graphical content, if I draw it graphically, you can hopefully see that this is, let's say, volume of CO2, because you know carbonate and acid will give you the product, and then this is time. So assuming the first one will give you like this, and then the reaction will come to a stop as the acid get fully used up because the carbonate is in excess. The second one is using 0.5 molar HCl, so it is slower than that, but you will get more product out because you have more of the limiting reactant that reacted. So it will be slower, so slower, but you will get more product out. So more product. Okay, but then if you could see the slope there, so this is initial rate. So you could see that this one is slower because less steep gradient. And remember, the gradient here refers to the change in the volume of product versus the change in time. So this is faster reaction because this has steeper gradient. All right, so going to the second changes will give you more products but slower reaction, which means we are looking at the correct option being option C. I should probably speed up a little bit, but I remember when I did this March 21 paper 1 for the first time a few months ago before I took down my videos. This paper 1 was actually one of the quite tricky one actually. So instead of having to do it so quickly and then not really getting the message across to the people who needed the help, so I mean, you can always skip the video if you want to, but I think the whole idea of my tutorial is to help learners see the whole point of how to address each and every question. All right, so we are given a Maxwell-Boltzmann distribution. So if I just draw whatever that the question we have given you, which is just like this, and you have number of particles with energy E, and you have energy E, and they have labeled this as EA catalyze, and they're asking you if the same reaction mixture but at a higher temperature. So at a higher temperature, the whole graph shifts to the right hand side, but the total area under the graph remains the same because your total number of particles remain the same. But as you can see, you have a greater area under the graph. That means you have more particles with energy greater than or equal to EA, and therefore rate of reaction increases. So the curve is unchanged. There's option A, which is wrong. The value of both EA catalyzed and EA decreases. So we know that EA doesn't change. It doesn't change with temperature. In fact, it doesn't change even with catalyst, but with catalyst you get a new lower EA. So I know that one is wrong as well. And then part C is also wrong for the same reason, because EA doesn't change with temperature at all. So we are left with option D as the only correct answer, where whether you're catalyzed or not catalyzed, your original EA remain the same. So if I have that thing there, so that would just be the EA. Well, I can do one better, I guess. If I just label this E here, and then this EA uncatalyzed, the original one. So it has to be option D as the only correct answer there. Question 12. So what we have is they're asking what is the observation when SiCl4 is added to water. You're going to get a hydrolysis of this period 3 chloride, and you will form SiO2, which will come out as an insoluble solid in water. It's a component of white sand, so you get a white solid or white precipitate, which is insoluble in water. And this reaction is very, very exothermic. Imagine you go from simple molecular with only 4 covalent bonds per single molecule, simple molecular, and then you go to giant molecular or giant covalent structure with a lot of strong covalent bond being formed. This reaction is hugely or largely exothermic. Your HCl has got low boiling point because it's a simple molecule. It's going to come out as misty or steamy white fumes due to the high exothermicity of the reaction. You also get like a white solid or white PPT because SiO2 is insoluble in water. So what we will get has to be option B, which describe both of these observations. Next question, question 13. Question 13 is about trends. If I look at option A is asking on first ionization energy. You should be able to sketch this kind of trend very easily on at your fingertip, because go up, go down, go up, go down, go up, all the way down. So they're looking at the third period, which is your case study. So sodium, magnesium, aluminum. The first drop is between group 2 and group 13. The second drop is between group 15 and group 16. So phosphorus and sulfur. This is P3 to P4, whereas this one was going from the S block to the P block. And then the highest one has to be argon, which is the noble gas, and then you go to the new shell, which is further away, and therefore it's slightly easier to remove this valence electron compared to the previous the group 1 metal in the previous shell. So the first ionization energy of phosphorus is greater than that of magnesium, so that is correct. Electron is lost from 3p orbital, that is not correct. So here your electron is from a 3s orbital. That is your first ionization energy. So you got to read the question carefully and not just jump to conclusion. So A cannot be the answer because of the reason being incorrect. I have a feeling that I'll run out of space there, so what I'll do is I will move this down here so that I can start off on a fresh new page. If I go for option B is to do with melting point. Again, you're expected to be able to sketch the melting point of the third period element. So sodium, magnesium, aluminum, they are getting stronger in metallic bond. Then silicon is all the way up there because it's giant molecular. So aluminium, magnesium, sodium. Do I know whether it's straight line like this? I don't know, and I don't care, but at least I know the trend is going upward as a result of stronger metallic bond. This one has a giant covalent structure, a lot of strong covalent bond to be broken. And then what happened then is it goes all the way down there to P4 being simple molecular. It goes up slightly to S8, and then Cl2, and then argon. Okay, so if you imagine this bit, these are just breaking the weak van der Waals forces because these are all simple molecular structure. So in terms of the total number of electrons in the molecule, so argon will have the least compared to Cl2, compared to P4, compared to S8, and that is why there's the order of the melting point. These are one of a couple of fixed essays that you will be expected to master AS level, but do not forget that anything from AS can and will be asked in your A2. So, the statement itself is already wrong. It said the melting point of phosphorus is greater than magnesium. Phosphorus is simple molecular. Simple molecule have low low melting and boiling point, whereas metals have giant metallic structure. So when you have metals, we will expect them to have high melting and boiling point. So I mean that statement itself makes B wrong as well. So this is a good recap of your inorganic chemistry. Okay, so in terms of atomic radius, so I hope you remember how to rationalize radii essentially. So radii, so as you go across a period, the size decreases from sodium all the way to chlorine, because generally speaking, the effective nuclear charge, the net attraction between the valence electrons and the nucleus, it gets stronger because shielding is roughly constant when you fill in across the same period, but you have more and more protons, so your valence electrons are more and more attracted towards the nucleus. In terms of ionic radii, they're going to follow this particular trend where the anion is bigger than the atom, but the cation is smaller than the atom. So these are all actually from the data booklet, but going forward, data booklet is being phased out from the exam itself, where data will be given in the actual question or as part of the question paper. So going forward, if you have these kind of questions, you really need to either know it or know how to find it from the data within your question paper. So it says atomic radius of phosphorus, these are atom. Okay, this is atomic radii. Green one is atomic radii, and green one is the one that they're asking because they did not mention about atom. So atomic radius of phosphorus is smaller than magnesium. That is correct. And we said that phosphorus have a stronger nuclear charge than magnesium. Shielding is roughly constant. So of course, this is not theory paper. But in a theory paper, they can ask you to explain it. So the effective nuclear charge, which is the net nuclear charge that the valence electron experience, is going to be stronger for phosphorus as a result of that. So key point number 1, number 2, and number 3 to get all the marks for a 2 to 3 mark essay question in paper 2 or paper 4. In terms of electrical conductivity, so electrical conductivity, as you can imagine, metal can conduct much better. That's why these are non-metals, the phosphorus onward. So you can imagine that if I have electrical conductivity on my y-axis, the metals will conduct much better. Sodium all the way to aluminium, because it can delocalize more and more of the valence electrons. Silicon is a semiconductor, so it's not zero conductivity, but then after silicon it drops all the way to zero because you have now non-metals. Phosphorus all the way to argon, these are non-metals. And therefore they do not conduct at all. Silicon is used in chip, a lot of computer chips, a lot of mobile phones and electronic devices. So they are semiconductors, so they do conduct slightly, but not as well as metals. So they say bonding changes from ionic in magnesium. So your reason, ionic in magnesium, something is wrong there already, because this is a metal. It has a giant metallic structure. So how can it have ionic bond? You can never ever have ionic bond in a metallic element. Question 14. So question 14 is about group 2 chemistry. They're asking you on barium and barium oxide. It's not asked in the question, but barium burn in oxygen to give you barium oxide. You gotta balance the equation, so 2 barium like that, and then the barium oxide can dissolve in water to give you barium hydroxide. So this is one way of getting barium hydroxide all the way from the metal itself via the combustion route. Of course, you could also react the highly reactive metal. As you go down group 2, the valence electrons are more and more easy to be lost. So barium plus H2O, there's a reactive metal, plus water is going to give you the metal hydroxide as well as hydrogen gas. That's going to give you 2 H2O in that reaction to balance the equation. 2 different ways of making barium hydroxide from the metal itself. This is a two-step reaction. This is a direct reaction between the reactive metal and the water. Anyway, so when you add barium metal to water, you're going to get rapid effervescence, because going down group 2, so down group 2, these valence electrons are more easier to be lost, and because they are easier to be lost since they are more shielded due to more and more shells, and you're doing a redox chemistry. This is barium 0, this is barium plus 2. So it's important that if it is much easier to be lost, then it's going to be a lot more reactive. You will get effervescence as a result of rapid production of H2 gas. So by saying that, option A and option C is out, you're left with option B. What I meant is option C and option D is in, but A and B are out because that will give you effervescence. And now in terms of the solution that you obtain, we know that group 2 hydroxide, hang on, not the Roman numeral in A level anymore. So group 2 metal hydroxide or group 2 hydroxides are becoming more solubles. They are more soluble down group 2. If they are more soluble down the group, therefore they are more basic or more alkaline. So it's going to be a strong base. So we're looking at pH 13, pH 14. So really we are looking at option D as the answer. So in question 15, we have an anhydrous white salt. So all the options given, they are all group 2 compound. So they are all going to be white instead of colored. And when you hit them strongly, we get a mixture of gases. So the hint there is mixture of gases. So this is plural. So that means we are expecting more than one gas. So if you think about decomposition of group 2 carbonate, M2 plus CO3 2 minus, so there will be MCO3 solid, group 2 carbonate, decomposes to give you the group 2 oxide. Oops, not a gas but a group 2 giant ionic structure. So there's your oxide there, and there's going to give you just one gas, which is carbon dioxide. Having said that, I can pretty much cross out the magnesium carbonate and barium carbonate. Can I? Let me think. Yep, I can definitely cross out the carbonate because there will only be one gas being produced, whereas if you have a group 2 nitrate, then they will give you a group 2 oxide as a solid, and you get 2 NO2 gas, which is a brown gas, and a colorless gas, which you can test with a glowing splint. So this is a brown gas, and that is a colorless gas. So there's no calculation involved here, but then we can cross out option A and option C because both of these has carbonate, and we're looking at something that will decompose in the presence of heat to give you more than one gases. So I'm left with option B and D. So we gotta think about this product, the solid remaining. The solid remaining is the group 2 oxide. When I dissolve that in dilute hydrochloric acid, remember that these are group 2 oxides, so they are what we call basic oxide. So they can react with acid, and when they react with dilute hydrochloric acid, and then you add in dilute sulfuric acid, so what we can have, if I make this just a little bit smaller so I can move the whole thing up. Do I want the whole thing up? Yep, I do want the whole thing to be moved up a little bit. Alright, so what we have is, we have this solid, so MO plus H2O, group 2 oxide plus H2O, give you the group 2 hydroxide. Sorry, nope. You want to add it with HCl, so that's adding with acid. This is basic, this is acid, you get MCO2 plus H2O. Not that it matters, because now what you have is you have M2 plus cation, and then you add in sulfuric acid, and you want to test the solubility of the group 2 sulfate. So this is a classic precipitation of group 2 sulfate, and you gotta know that barium sulfate is a classic white PPT, even from your O-level IGCSE practical component. So this solution, so this substance has to contain barium, because you added sulfate to it and it gives you a precipitate. So barium must be the cation, and nitrate must be the anion, so we're looking at barium nitrate, and the correct option would be option B there. Question 16. So we have chlorine gas reacted with aqueous sodium hydroxide, and you specifically want this thing to have what do we want? We want chlorine -1 and chlorine +1 as the products. So we do not want an extreme disproportionation. We just want mild condition for the disproportionation. This is a case study under group 17 chemistry that's related to one particular species, chlorine plus NaOH. That is chlorine in zero oxidation state going to not HCl. Instead, what you get is NaCl. This is chlorine -1, and you get NaClO. This is called sodium chlorate, bracket Roman numeral 1, because that is chlorine +1 oxidation state, +1 for the group 1 metal, +1 for the chlorine, -2 for one of the oxygen. That compound doesn't have oxidation state because the compound has 0 overall oxidation state. I'm going to balance the equation with 2 sodium, so I have 2 NaOH there, and I have 2 chlorine, I have 2 oxygen, and I have 2 hydrogen there. Alright, so under these conditions, under this mild condition, we're looking at cold dilute alkali, and of course the color of the solid silver salt with the chlorine in oxidation state -1. So chlorine -1, that is going to be your Cl minus aqueous, plus the silver nitrate, which is Ag plus aqueous. This gives you another classic precipitation ionic equation, something that they like to ask even from your O-level or your IGCSE 14 to 16 years old chemistry. So we're looking at option A as the only correct answer. Question 17. So question 17, they are asking you on the reaction of corn sulfuric acid with the iodide. So if we have this oxidizing ability or oxidizing power, we know that chlorine is a stronger oxidizing agent than bromine than iodine. I do not have actual values, neither do I need to, but I know where my stuff is. Corn sulfuric acid is a weaker oxidizing agent than chlorine, so Cl minus will not undergo any redox reaction with H2SO4 because it cannot be oxidized by corn H2SO4. However, because this is a stronger oxidizing agent than Br2, so corn sulfuric acid can oxidize Br -1 to Br2. The same thing with I -1, it will give you to I2. But in terms of the sulfur +6 stops at sulfur +4, which is SO2 product. As for this one, because this is a much weaker because the I- is a stronger reducing agent, and there's a bigger difference between the redox ability. So the sulfur there, the I- can reduce the sulfur even further. So you can get sulfur +6, go to sulfur +4, go to sulfur 0, go to sulfur -2, which is the minimum oxidation state for group 16 elements, sulfur. So that product there would be SO2. That product there is just elemental sulfur, or just S8 if you want to. And then there's your hydrogen sulfide, which is H2S, sulfur -2 oxidation state. This smells a bit like rotten egg, so there's not a very good smell for you at all. So I guess in terms of what this one is, if you look at which statement is correct, so with iodide, H2S is the product of a reduction reaction. So all of these is what you call reduction, because they keep on decrease in oxidation number of the sulfur. Alright, and having said that, this is the oxidizing agent. So corn sulfuric acid can be the oxidizing agent, but not with chloride, but with bromide and iodide. So iodide ions are stronger oxidizing agent than sulfate. That option B is definitely wrong. sulfur atoms are both oxidized and reduced. That's definitely wrong, because sulfur, there is already sulfur plus 6 in the sulfuric acid formula, and I leave there as an exercise for you to do on your own. It doesn't go higher. Plus 6 is the highest or maximum oxidation state goes to. That's why option C is definitely wrong. And the sulfur atoms are not oxidized. In fact, to go from sulfur plus 6 to sulfur plus 4 to form SO2, option D, something is wrong because of that word called oxidized. It should be reduction, reduction, reduction. So, well, actually, did I mention the answer yet? Nope. So the correct answer, there must be option A, because of what I said about the other options not being correct at all. Question 18. Question 18 is about a redox chemistry again, but it's to do with environmental chemistry. So this is to do with catalytic converter. So what is happening inside a catalytic converter? Dirty gases become clean. Dirty gases become, well, not really like clean, but you know, cleaner gases, less toxic gases. So you can imagine that NO will go to N2, NO2 will go to N2. So these are nitrogen plus 2 oxidation state. These are nitrogen plus 4 oxidation state. These are nitrogen 0 oxidation state. From this both going to this one, this is reduction. From something that contains oxygen to you losing the oxygen. You can also think about loss of oxygen. That is going to be reduction. Alright, so NO is reduced, NO2 is reduced, so that means A is out, B is out. What happened to CO? CO plus half O2 will give you CO2. This is just to complete the combustion, and this is basically to completely oxidize the CO to CO2. So this is oxidation. Alright, you can also, in terms of oxidation number, there's carbon plus 2 because you only have one oxygen with oxygen minus 2. And this will be carbon plus 4 where the oxygen is still minus 2. But you've got 2 of the oxygen, so 2 times minus 2 is going to give you minus 4. In terms of unburned hydrocarbon, so unburned hydrocarbons, you can burn them completely. And that will give you X plus Y over 4. O2 give you X CO2 plus Y over 2 H2O. In terms of the algebra, I explained it earlier in one of the question in this particular paper. So you can think back, or you can scroll back and rewind back to that part of the tutorial video. So this is definitely oxidation because it's actually to complete combustion. Complete combustion involves burning in excess oxygen. So it is an oxidation process. So all of these would tell us that option C is the only correct answer. Question 19. Question 19 is a strange one. But then what they are saying is if you have methyl ammonium chloride, of which they give you this equation. So this is methyl. And this is methyl amine because it's NH2. You react it with acid, and then you will get a salt where the base uses the lone pair to accept the H plus from the acid, which donates the H plus. So that donates the H plus, that accepts the H plus, and what you get is you will get NH3 and then a plus. The nitrogen form one bond to the carbon, and 3 other covalent bond to each of the hydrogen there, and you get Cl minus. The charges balance out, the atom balance out. This is a classic acid-base neutralization reaction. So what they're saying is that this behaves just like ammonia. If you think about ammonia, ammonia is NH3, NH3 plus HCl will give you NH4 plus and Cl minus. And then they're saying that what happened when methyl ammonium chloride is reacted with sodium hydroxide. I will first think about ammonium. Ammonium plus hydroxide. This is the base. It will accept H plus. This will loses the H plus because this is acting as an acid. This is acting as a base. So the base accept the H plus. This loses the H plus, and you will get NH3. And what you get now is H2O. This is ionic equation. So make sure that you know you can write ionic equation really well. That is not what the question is asking. In fact, what the question is asking you is, what about this thing here? NH3, CH3 plus. So what you have now is the same reaction. So instead of NH3, what you get is CH3, NH2, and then the OH minus will also accept the H plus. So one of your product One wave product will be this, the other product will be this, and don't forget that this come with Na plus, and this will have come with the chloride, so you will also get sodium chloride, because as you know, there is a word equation where you have ammonium salt. So if you have ammonium salt plus any metal hydroxide, so hydroxide comes with a metal, what you will get is you will get a metal salt, and you will get NH3, and you will get water. This is an ionic equation. We don't show the metal salt because it's soluble, and that is why the correct option is option D, because they're asking for all the products, of which one of the product will be the metal salt, which is the sodium bit from the sodium hydroxide, the chloride bit from the methyl ammonium chloride. So you also get sodium chloride as a product. Question 20 is about organic chemistry. It's about identifying chiral center. So if you look at it, you can hopefully see CH2CO2H, and then COHCO2H, and CH2CO2H. You can hopefully see that, you know, this bit and this bit are the same. All right, so this carbon is bonded to two groups that are the same, and this carbon there has two hydrogens, so this carbon cannot be chiral. This carbon has a carboxylic acid. A carboxylic acid does not have 4 covalent bonds. Well, actually what I mean is it does not have carbon with 4 single covalent bonds. In fact, it has a double bond there, which is 1 sigma and 1 pi. So you know you cannot have chiral center when you have a carbon which is not forming 4 single bonds. So this is citric acid. Citric acid will have 0 chiral center. And then what you have now is you have isocitric acid. Isocitric acid is an isomer of citric acid, so you have CH2CO2H, CHCO2H, and you have CHOHCO2H. So hopefully you can see now top bit is different from bottom bit, and most people can spot that this is chiral. But then some people forget to check for every single carbon, because now this carbon, this other one is also chiral, because that carbon has 1 hydrogen, 1 OH, 1 CO2H, and this is different. This one, top and bottom different, hydrogen and CO2H different, so you got 2 chiral center there. This carbon cannot be chiral for the same reason I mentioned. It's got 2 hydrogen, they are the same. This carbon cannot be chiral because it hasn't got 4 single covalent bond. So there are 2 chiral center for the isocitric acid, which means we are looking at option D as the only correct answer. Question 21 say how many tertiary alcohol. So the key term there is tertiary alcohol. The carbon with the OH is bonded to 3 other carbon. You're looking at C6H14O. So the first thing you should do really is think about tertiary alcohol. The carbon with the OH, is bonded to 3 other carbons, so R dash. They could be the same or they could be different, doesn't matter. As long as we fulfill up to 6 carbon, there's only 1 oxygen, therefore it's only 1 OH, which is a tertiary alcohol. Let's start drawing, and if you try to draw or just display a formula, you're going to be wasting quite a lot of time, so try draw skeletal formula. I'm going to draw with just 3 carbon like that. 1, 2, 3, 4. I'm missing 2 more, so what I can do is 1, 2. 1, 2, 3, 4, 5, 6. And when I have 3 carbon like this, I can also think about forming what I call a chain isomer, because you can branch out straight chain and also branch isomer. So this and this, the relationship is structural isomerism, specifically chain isomerism. 3 carbon can be branched out as like that. What else can I see? If I have 1, 1, and 3, I could also have 1, 2, and 2 like this, because 1, 2, 3, 4, 5, 6. We are not looking for chiral, we are looking for tertiary. The carbon with the OH is bonded to 3 other carbon. So this is 1 carbon, 1 carbon, 3 carbon, 1, 1, 3, 1, 1, 3, 1, 2, 2. So 1, 1, 3, Actually, I don't want comma because that's confusing. 1 plus 1 plus 3. When I say 1 plus 1 plus 3, I also have one central carbon, so don't forget to add the central carbon. That will give me 6, and what I have here is the central carbon plus the central carbon, meaning this central carbon. Then I have 1 and then 1 2 1 2, so 1 from the center and then 1 2 2. That will give me 6 carbon. What else can I say? So 1 1 3 1 2 2. I think that's all really. I can't find any other option because you can try 2 1 2, but it's the same combination, isn't it? So there are only 3 different isomers, and therefore the correct option must be option C there. So draw and see for yourself. Question 22. So this thing is about a bromo compound. You react bromine with hydrocarbon. So if I just draw the skeletal formula, no, actually I'll probably draw the structural formula given as such. So CH2Br, CH3, CH2Br. So what we have here is we have a halogenoalkane. The carbon with the halogen is bonded to one other carbon. This is the carbon bonded to the halogen is bonded to one other carbon. This is a primary halogenoalkane. The carbon with the halogen is bonded to one other carbon. This carbon with the halogen bonded to one other carbon. This is also a primary halogenoalkane. Okay, so these two bromine, they are not next to one another. Not next to one another. If you think about the position, this is carbon 1, carbon 2, carbon 3, let's say. Okay, so they are not addition reaction, because when you have alkene and alkene, when you add there and there, you add across double bond or triple bond, then your Br and Br will be next to each other. So here you can see they are not next to each other because there's one carbon in between with no Br on it. So this cannot be addition. So this tells you that addition, if you say addition reaction, so it's straight away out, A is out, B is out. So we're looking at substitution reaction, which is C or D. So you can be thinking about what is going to happen. What's going to happen here is perhaps we can think about, what can we think about here? Substitution reaction. So could it be substitution reactions? Then we want to form this, but we don't have alkene, so it has to be a free radical substitution. If you think about it, it's like this, and then what you have now is like this. So what has happened there is this one with the CH and this one with the CH. Now with the CH is gone. Just now you have 3 CH, now you have 2 CH. Okay, of course then it's just plus 2 HBr. This is plus Br2. This is UV light. And this has got to be one of the substitution for the CH of alkane. So this is just your free radical substitution. Your case study involving the chemistry of a non-polar hydrocarbon, which is option D. Question 23. So this is kind of a repeat question I've seen a couple of times. So they give you the skeletal formula of it. What is important is we react this with sulfuric acid first of all. So you have a lot of double bond. That doesn't look right. Is that right? Yep, that looks okay. So you have an ester. So this is an ester linkage. Hope you can see the ester linkage there. So there's your ester. The rest of these are alkenes. When you hydrolyze ester, this is the bond that you break. That will give you the carboxylic acid. This will give you the alcohol. So when you have H2SO4 and you reflux it, then that will give you the double bond is untouched. But what happened then is O and OH plus HOCH3. This is the main product. This is the X, and X is going to be reacted with sulfuric acid. So now, oh no, you already reacted with sulfuric acid. This is actually your hydrolysis of ester in acidic condition. And then I react that with hydrogen. Hydrogen will add onto double bond, but hydrogen in the presence of nickel catalyst will not hydrogenate carbonyl bond of a carboxylic acid. Will not work. to add onto CO of carboxylic acid. Alright, so what we are expecting is R. Well, in fact, I'll lose all the double bonds. So it's just single bond like this, and single bond like this, and the carboxylic acid remains. So we're looking at answers that does not have carbon double bond, which all the answer does not have carbon double bond, and we're looking at something that still has carboxylic acid. So there's option A or D, but then you didn't add H2O onto double bond, you add molecular hydrogen onto double bond. So this must be option A, which is the correct answer. Question 24, what do we have? 24 is about the product. You get a ketone product. So ketone as the oxidation product. This means when you work backward, therefore, you're looking from secondary alcohol. The carbon with the OH is bonded to two other carbon. Alright, so there are four options given there. So A is pentane 1-ol. So pentane 1-ol is 1, 2, 3, 4, 5. You can see that the carbon with the OH is bonded to one other carbon. This is a primary alcohol. When you oxidize it, you can get aldehyde if you heat and reflux. But this question says heat and distill, you can get aldehyde. But this question says reflux, and your reflux it will acidify dichromate 6, which is orange, and your dichromate 6, chromium plus 6 in Cr2O7 2 minus will go to chromium plus 3 in Cr3 plus. Aqueous, the color change is something that they like to ask you, not just in theory paper, but also in paper 5 or some other alternative to practical kind of paper. So then the primary alcohol. In reflux, what you will get is you will get carboxylic acid. You get a 5-carbon carboxylic acid. They didn't ask you, but they could have asked you in a theory paper, like paper 2, for example. Next one, 2-methyl butane 1-ol. I will start from butane 1-ol. This is 1, 2, 3, 4. But, because 4 carbon straight chain, butane 1-ol, OH at position 1, 2-methyl. Methyl is 1 carbon, so you have 1 carbon chain there. So again, this is a primary alcohol because the carbon with the OH is bonded to one other carbon. You can imagine that under the same reflux condition, you're going to get carboxylic acid. Option C, so I draw but. I should draw but, not pent. So 1, 2, 3, 4. But 10-2-ol, and I got 2-methyl. And hopefully you can see that this is a tertiary alcohol because the carbon with the OH is bonded to 1, 2, and 3 other carbon. This is a tertiary alcohol, and these are not oxidized because tertiary alcohol has the carbon with the OH bonded to 3 other carbon, so there's no other hydrogen here. If you don't have hydrogen here, you cannot lose what you never have to begin with. You want a ketone? Well, option D must be the answer because option A, option B, option C does not give you ketone. If I try to draw butane 2-ol, this is butane 2-ol, 1, 2, 3, 4. Doesn't matter if I go this way or this way, it doesn't, as long as I number them correctly. Butane 2-ol, 3-methyl, butane 2-ol. So the carbon with the OH is bonded to 2 other carbon. The carbon with the OH is here, bonded to 2 other carbon. There's 1 hydrogen there. When you oxidize it, you will get ketone, where this is a carbonyl, it's bonded to 2 other carbon, so it's a ketone product. Option D is the correct answer there. Question 25 is about what do we have? We want only 1 hydrocarbon. Hydrocarbon meaning only containing carbon and hydrogen atom, and the key thing is not just hydrocarbon, but it's 1 product only. It's double elimination. So we started by C5H10Br2, so we gotta take away 2 NaBr because we are using aqueous sodium hydroxide. Sorry, not aqueous, but actually we need NaOH in ethanol in order to favor elimination. So the classic elimination versus substitution, this is in ethanol, and also you need reflux in order to do elimination. If we go through option A, so it says 1,5-dibromopentane. So pentane, 1, 2, 3, 4, 5. 1,5-dibromo, so 1 bromine at position 1, 1 bromine at position 5. When you want to do elimination, you want to get back the double bond. So we look at the carbon with the halogen, when then we go to the next carbon. We go to the next carbon. The next carbon there is this one. It's got hydrogen. So what you would do is you get a double bond there. And the same thing there. The carbon with the halogen is there. So I want to form a double bond by removing the hydrogen from the next carbon. So I will remove these and I'll remove these. So what I'll get is double bond between 1 and 2, double bond between 4 and 5. There's just one product. I'm pretty sure I get my answer already, which is option A. Which means the other options are wrong, but you know, what I'll do very quickly is just to go through the other options and see what could you get as the product. So you get pentane as well, but you get 1, 4. So 1 and 4. So as you could see here, this one will give you the double bond there. So you will get double bond like this. But the next one, this is a tricky one. You can get the pink color from the hydrogen here. So there's 2 hydrogen options. They are different. They are different from here, because here you have 3 different hydrogen. So this hydrogen and this hydrogen is different. So you can get double bond there. So that would be like this. But the pink one will give you this one, this one, this one, like this. But this is trans because it's a geometric isomer. You can also get cis. So altogether, you get 3 different hydrocarbon products, and they wanted 1 hydrocarbon product. I could go on and on. So if I just very quickly do dibromopentane, 2 and 3. So if I have 2 and 3, so again we go through that thing. The carbon with the OH is with the Br is there, so I could get a double bond there. I could get a double bond there. So like this, and then this thing can have cis or trans. So what I've shown there is a trans because this group and this group are on opposite side. So I could draw that. I could label that as the trans. But there's no cis or trans here because this is a CH2 terminal group. Okay, so that is the cis isomer. So there are 2 products there, and we wanted 1 products. Last but not least, just to complete the story, I have 2, 4, 2 and 4 dibromopentane. So if I am here, remember that this hydrogen and this hydrogen are different. So I could get double bond there. I could get double bond there. So like this, like this, like this. This is the trans product, which means I could also get the cis product. So like that. That is very badly drawn actually. Like this, like this, like this, like this. So this is a cis product, this is the trans product. What else can I get? I can also do the hydrogen there, so that will give me like this, and there will be no cis and trans there. So yeah, you do get 3 different products as well. 3 different hydrocarbon products, which include the geometric isomers. So in the next question 26, we have this thing where X plus HCN in the presence of KCN. They didn't say catalyst, but this should remind you that this is a nucleophilic addition mechanism, because based on what we can see here, we are doing HCN addition and we are not using KCN as our reactant, which is why KCN is not present as a reactant on the left hand side. Instead, they put KCN on top of the arrow. So we're looking at nucleophilic addition, and therefore we're thinking about a carbonyl C double bond O. So we're looking at this thing that has R1, R2, and the original OH comes from the ketonic group. So C double bond O, R1, R2. This is a ketone where the carbonyl has the carbonyl carbon is bonded to 2 other carbon, and we're looking at nucleophilic addition. So this means the only correct option will be option C there. Question 27. So question 27, I remember this was a very difficult question. Difficult in the sense that it's difficult to actually make sense of it, but it's not entirely a difficult chemistry at all. So they're asking for correct statement. And what is confusing about this is basically the idea of using, the idea of NaBH4, where all the hydrogen there is hydrogen 3. This is a heavier isotope of hydrogen. Only for the borohydride today we have this heavy hydrogen where it says all the hydrogen there is like that. So we can be thinking about Na, boron, and it's a heavy hydrogen where we have 4 of it. So again, this is a nucleophilic source of a hydride. A hydride is like that, but this is a heavier version due to the heavier isotope of hydrogen. So this question is all about mechanism actually. So if I draw CH3CH all like that, this delta minus and delta plus from the hydride itself with negative charge, from the lone pair attacks the delta plus carbon, and then this will break the carbon oxygen double bond. There's the first step in the nucleophilic addition reaction. So you add in the H. There is this is a 3H, and I should probably use a different color to represent the other H here, which is a normal H. Tell you what, I'll probably do this in red so we can see the difference. Style it and let's make it red. But I want the other one to be blue, so that we are not confusing the original hydrogen with the red one, which is the one from the borohydride, which is this red color one. So what's going to happen now is this is done in the presence of water. So you have water which does not have the heavy hydrogen. The heavy hydrogen comes from the heavier isotope of the hydrogen come only from the borohydride. The next step is just H and OH. So they will take away the H from the borohydride used in water, essentially. Okay. So you will get OH like this. I forgot I should really use the red color one to represent the H there. But of course I also have a normal H here, and I have a normal H, and normal H. So what can we say? So what happened with the OH minus is I will get the normal H like this. And what can we say? So here you have the heavier hydrogen, which is the red color one. So this hydrogen 3, they come from borohydride, but the other hydrogen were originally there already, including the hydrogen that you take in from this oxygen lone pair is from the water, and that doesn't contain that one. So what can we say? We have this thing here. So what can happen then? You also have H2O. So let me see. This thing is about oxidation, right? So compound Z is then oxidized back to ethanol and water. So this is Z. This is Z. This is the very confusing thing about this. So what happened then is if I write Z, which is C2H6O, when I oxidize it, I can get back the aldehyde if I heat and distill immediately. So heat and distill immediately because it's a primary alcohol. So you want to stop at the aldehyde, you heat and distill immediately to prevent oxidation all the way to carboxylic acid. Out of the 4 statements, so what is confusing about this is if I look at what Z is, so you have that, but you also have one of the heavy hydrogen. When you oxidize it, you have the original hydrogen there. So you can lose this hydrogen, or you can lose this hydrogen when you form the aldehyde. So essentially when you do oxidation, you can either have you can either have that and then a aldehyde like this, where the hydrogen could be this one, meaning this one, meaning you have lost this isotope 3, or it could also form the one where you lose the other hydrogen, and therefore this one remains. So both of these could be formed, and as a result of it, your other products as given in the equation. So to form this, you will have lost this hydrogen 3. So you know your other product will be 3 hydrogen, 1 hydrogen, oxygen. Whereas for the other one, then you will get 1 hydrogen, and all. Remember, this is still H2O, this is still H2O. It's just that this H2O is slightly heavier than this because it's got the isotope 3 there. So pretty much A is the only correct answer, because both the ethanol as well as the water, they can contain the isotope 3. So this is the isotope 3 in red there. So you could get a mixture of these and this as the product, and therefore you could get a mixture of these and these as the H2O products as given in the equation. This is the very reason why option A is correct. If you go through option B say ethanol, the aldehyde, is the only product. So what is wrong about B is talking about only. So the word only is wrong for B. In C, the word neither is actually wrong, because both of these products, one of them will contain the hydrogen 3, one of them will contain the hydrogen 3. And then option D, it says water is the only product that will contain the hydrogen 3, and that is entirely wrong, because you could get aldehydes that contain the hydrogen 3 as well. So option D is wrong because of only. So this comes down to the mechanism as well as understanding what happened in the follow-up oxidation in terms of loss of hydrogen. Question 28. So what we have here is ethane dioic acid. So ethane dioic acid is a dicarboxylic acid with 2 carbon. So you want to form aluminium ethane dioate. So after you lose the 2H plus, then you're going to get ethane dioate anion. So this is called ethane dioate anion. So it's a dianionic anion with C2O4 2-. So when you combine it with Al3 plus and C2O4 2-, your job is to balance out the charges. How many of each do you need? So this comes back to your IGCSE or your O-level chemistry. You bring down the number, which is 2. You bring down the number, which is 3. Whatever is on the left here represents Al3 plus. That means 2 of the Al3 plus, and then 3 of the C2O4 2-. If you have 3 of them, then you're gonna get minus 2, minus 2, minus 2, give you minus 6. 2 of these plus 3 and plus 3 give you plus 6. Plus 6, minus 6, the charges get cancelled out, and that's the whole idea of forming ionic compound, where the charges get cancelled out, and this is option D there. Question 29. So you want butanoic acid as a product. So butanoic acid is a 4-carbon acid. It's a 4-carbon carboxylic acid like that. So if we look at option A, it's a butyl ethanoate. So butyl ethanoate means you have a 2-carbon carboxylic acid. So hang on, I don't want that. I want to draw the ester first. And then on the left hand side, you got 1 carbon and 2 carbon. This is the ethanoic acid. They give you ethanoate. So it's 2 carbon. And then butyl is 4 carbon. So you start off from the alcohol, and then you can have 1, 2, 3, 4. So as you could see there, this is a 4-carbon alcohol. So it is not acid. So it is not butanoic acid. You want butanoic acid, you can only get ethanoic acid there, and that's why that is wrong. If you look at option B, again we have butyl ethanoate. So it doesn't matter acid hydrolysis or base hydrolysis, butyl ethanoate does not give you anything with 4-carbon acid. They only give you 2-carbon acid, so you will not get butanoic acid as one of a product. So our answer really is just C or D. But then you also need to consider acid hydrolysis versus base hydrolysis. This is a carboxylic acid group, so it's acidic. It will get deprotonated in a neutralization reaction if you use base or alkaline hydrolysis. So D is obviously wrong, because D, if I do alkaline hydrolysis, ethyl butanoate, ethyl butanoate. So this is 1 2 3 4 butanoic acid, and then ethyl. So this is the ethyl. This is the 4-carbon carboxylic acid, ethyl butanoate. So that is the ester bond that I hydrolyze. If I do it under acidic condition and reflux, I will get carboxylic acid, which is one of my product, and I'll get ethanol as the other product. If, however, I choose to do alkaline hydrolysis, so in the presence of aqueous and LH and reflux, I will not get carboxylic acid. I will get the salt of the carboxylic acid where the acid gets deprotonated, but then the aliphatic or the straight chain alcohol does not get deprotonated, and you will just get ethanol as a product as well. But this is option D. Alkaline hydrolysis does not give you the butanoic acid. You need option C that will give you the butanoic acid as one of the product. Question 30. So this is an infrared question. So the first thing we look at is when reactant X is treated with suitable reagents, it gives you two things. If you look at X, X will give you Y, X will give you Z. If you look at the infrared of the X, it has no broad OH at around 3200 cm minus 1. In fact, it is the sharp one. So this is the absence of broad OH. So therefore, no OH bond. So there is no OH bond. There's factor number 1. Factor number 2, really, we don't have any carbonyl because we don't have any strong band around 1800. So, it doesn't have any C double bond O at around 1600, 1700, something like that. But then when you react with something and you get product Y as well as product Z, that doesn't look like a straight line at all. So product Y has no OH. You are looking at strong, broad absorption at around 3300 or somewhere around 3000 cm minus 1. There isn't a strong one at all for product Y. But then for product Z, it has OH because you have a strong broad absorption at around strong broad absorption at around 3000 cm minus 1. So it has OH for Z, and both of it, this one has C double bond O. You can tell that it's roughly at 1800, so give or take 1800 wave number. This one also has C double bond O, but this one is at a slightly different wave number. It's around 1700 wave number. So it has C double bond O and OH for Z. Y has no OH, but it has C double bond O. So they're asking for which row could be correct. So the first thing I do is I look for C double bond O, but then this one has no OH. So if you look at Y, you can tell option C is definitely wrong because option C says that Y is ethanoic acid. Ethanoic acid has carboxylic acid, so C is wrong. If you look at X, and option D says propyl propanoate. Propyl propanoate is definitely wrong. So option D, where X is propyl propanoate. So 3 carbon alcohol, 1, 2, and 3. This is a 1 carbon, 2 carbon, 3 carbon acid. Propyl propanoate. This is an ester, and it has got a C double bond O, but we said there's no C double bond O in X at all. So that's why we can cross out option D. So far, option C and D are out, and you can look at option A and B, where Y is said to be both propanone, so there's no point looking at option A or B based on Y alone. But let's have a look at Z. Z has OH and it has C double bond O, so cannot be butanone. Butanone is just a ketone. A ketone basically only has C double bond O, but it has no OH. This one has OH, so we know that option A is definitely wrong. Option A is definitely wrong. So A is wrong, C is wrong, and D is wrong. So you're left with option B. That must be the correct answer. Now we're left with the last 10 questions of this pretty long paper 1, so perhaps I should speed up a little bit. There's a bit of logic that goes around these last 10 type of questions in section B, which I have read that they are going to phase out of the current new syllabus. So going forward, you have a slightly longer paper 1 in the absence of these last 10 questions, where they're probably easier to score these kind of last 10 questions because it's by logic. You check option number 2 first. That's probably why they're giving you extra 15 minutes, because there'll be more questions for you to think about rather than working by logic alone. So question 31, you have H2 plus I2 going to give you 2HI, gas, gas, and gas. They're talking about Kc as well as Kp. So Kc is going to be the concentration of Hi square over H2 to the power of 1, and then I2 to the power of 1, whereas Kp is to do with partial pressure, so it's partial pressure of Hi square over the partial pressure of H2 times the partial pressure of I2, like that. So which statements about these equilibrium constants are correct? What can we say? So what we have is we have the mole at equilibrium. So they've given us some values: 2.27 mole for H2, 2.84 mole for I2, and what's the other one? 17.15 mole of Hi. Then they say the volume is going to be 1 meter cube. It's a closed cylinder, so they are in dynamic equilibrium. 764 Kelvin, 141 kilopascal. Doesn't look like anything has changed at all in terms of pressure and temperature. So let's try and work out Kc first of all. So Kc is equal to, if I just copy all of this down there, then I can just rub that out. So Kc is equal to that, and then let's sub in some value. So concentration is in mole per dm cube. Concentration is in mole per dm cube. So let total V be V. I guess let total V be V. Let total volume be V. Then Kc is equal to, if I sub in the value given in the information above there, so 17.15 square over 2.27. Oops, sorry, I forgot the volume. This is mole over V square. 2.27 over V, 2.84 over V. The 1 over V square over 1 over V square get cancelled out. So what you get on your calculator is going to be 45.6. There's 3 significant figure. So there's your Kc. I wonder if we can work out Kp or not, but this one definitely tells you option 2 is correct. So there's no unit there. Of course, you can check option, this is option 2 by the way, so I check option 2 first. Now I check option 1. So what's option 1? So I say Kc has no unit because it's, as you could see, mole per dm cube, the whole thing square, divided by mole per dm cube, divided by mole per dm cube, the unit cancel out. Kc has no unit. You can try and have a look at the expression for Kp, but you should hopefully see that the unit actually get cancelled out as well, because even though these are partial pressure, so let's say your unit is Pascal, or it could be Newton per meter square, really up to you. These will be Pascal and Pascal, and that will give you no unit also. So pretty sure that option 1 is also correct, so nice and easy there. The other question really is, how about option 3? Okay, do I really need to work out what this one means? So the total mole at equilibrium. So far we have just worked out the value of Kc. I'm going to work out the value of Kp now. Total mole at equilibrium is going to be 2.27 plus this. So 2.27 plus 2.84 plus 17.15. That gave me 22.26. So this is total mole. I'm going to cut that and paste it down here. Alright, so yeah, I mean, you can work out the partial pressure, 22.26. So what we have is partial pressure is going to be 2.27 divided by the total mole at equilibrium, which was 22.26. As a result, summing up the total mole at equilibrium. So 26 times what's the P total? Time 141 kilopascal, and then this is 2.84 over 22.26 times 141 kilopascal. This is 17.15 divided by 22.26 times 141 kilopascal. You can sub all of that in, get all the value. You can sub all the way into this expression, and you will get the Kp exactly equal to Kc. I have done that. You can do that and check for yourself. And the Kc equal to Kp in this instance, which means that option 3 is correct. And earlier we talked about option 2 was correct. Option 1 is correct, and option 3 is correct. So therefore, all are correct. If all are correct and relevant, so there's option A that we are looking at for question 31. Question 32. So what we have here is CH4 gas plus 2O2 gas going to CO2 gas plus 2H2O liquid, and you have carbon solid plus 2H2 gas plus 2O2 gas, and this thing there is delta Hz. This thing is given as combustion of CH4 gas, and this thing is given as the formation of CH4 as a gas. Alright, so stat symbol is very, very important as its direction in this enthalpy or energetics topic. So we can be thinking about a couple of things. Alright, so what is delta Hz equal to? Thinking about this, going from here to here, what we can see is we are burning the carbon completely and we're burning the hydrogen completely. So this is equal to enthalpy of formation of CO2 plus 2 times the enthalpy of formation of H2O. Because these are all elements, if you have the enthalpy of formation of the products, so this is equal to the enthalpy of the formation of the products minus the enthalpy of formation of the reactants. But since all the reactants are elements, the formation of elements is going to be 0, which is why it's just the enthalpy of formation of the products, where you form 2 mole of the water and 1 mole of the CO2 in this balance equation. Alright, so what can we learn from this exactly? This thing here, the delta H combustion of carbon is equal to the formation of CO2. If you write an equation for this, it will make entire sense, where this is the balance equation. You could be thinking about combusting 1 mole of carbon, 1 mole of substance in excess oxygen, or you can be thinking about forming 1 mole of the substance from its elements in its standard states under standard conditions. In terms of the formation of water, so the formation of water is going to be equal to the combustion of hydrogen gas. Again, you can write a balance equation for this, and you get H2O liquid and half of oxygen and 1 mole of H2 like that. So we can see the relationship like this. So 2 times this formation of H2O is equal to 2 times the combustion of hydrogen. So as a result of that, let's have a look at option 2. Option 2 says combustion of carbon, which is this, plus 2 times the combustion of hydrogen. So option 2 is correct based on what we have said, that this is equal to this. So you can substitute this with combustion of hydrogen times 2 plus the combustion of carbon times 1. Option 2 is correct. Option 1 is correct because we are going this way, which means you could do Hess law and go this way. So that's going to be equal to the enthalpy of formation of what am I doing? Is that correct? Number 2 is already done. Number 2 is done. We're looking at number 1, which is the formation of CH4 plus the combustion of CH4. So option 1 is also correct. All right. But how about option 3? What do we say about option 3? Option 3 says there's enthalpy of combustion of CO. So CO is carbon monoxide, and then it's a plus 2 times the combustion of H2 as a gas. So they're saying that when you burn the CO completely, you know, you can get the CO2 as well. However, we cannot accept this thing as equivalent to this expression, because when you talk about the combustion of CO, it's how can I say this? Yeah, CO essentially is a result of incomplete combustion, and you don't have CO in this equation at all, so you can't incorporate this into here. Someone did ask me about this before, and I did have a proper explanation for it before, but I don't think I should spend too much time talking about it here, simply because I've spent long enough in this tutorial. But if you're interested, I can outline it for you again. The shortcut really is to think about it that this is a result of incomplete combustion, whereas here is all about combustion, is all about combusting in excess oxygen such that we don't have incomplete combustion. So that will give you 1 and 2 being correct. That means is option B. Should probably go on to a new page actually. Let's see, question 33. Question 33 is talking about gaseous reactions do not obey ideal gas equation. So we are looking at assumptions that break the ideal gas equation, and this is at high pressure. So at high pressure, so the volume of molecules, if we look at option 2, they say the volume of molecules increases at higher pressures. The volume of molecule is a larger proportion of the total volume. At higher pressure, the volume of the molecules. Okay, option 2 looks confusing. I don't know what option 2 is all about, but let me check option 1. Option 1 is say as pressure increases, molecules have more energy. So sometimes I do not always have to check number 2 first. So now I'll check number 1. I can tell you something is wrong with number 1. More energy. Okay, so your Maxwell-Boltzmann distribution diagram is a energy distribution. Okay, it's an energy distribution diagram. Only temperature, your graph only changes its shape only when temperature changes. So only temperature changes energy distribution. Nothing else ever changes energy distribution at all. So when they say pressure increase, molecule having more energy, is entirely wrong. There was actually option 1. So option 1 is definitely wrong. If option 1 is wrong, you only have one answer, which is option C. So 2 and 3, without me even checking the other options at all. Question 34. So it say which one can accept. So accept is a key word there. Accept lone pair of electrons. So you're accepting lone pair of electrons. So we're talking about electron pair acceptor. Electron pair acceptor is also known as electrophile because they are looking for electrons. Okay, hungry for electrons, or we say electron deficient, not enough electron. That's why you're looking for electron. You like electrons because you are accepting a pair of electrons and you're forming dative covalent bond. If I check option 2, so there is H plus. If you think about the most common reaction, which is acid plus base, so NH3 uses the lone pair to pick up the H plus, you're going to get NH4 plus. This basically looks like this. H, this is trigonal pyramidal with 107 degree. Now you add in the H plus, a dative covalent bond with the lone pair from nitrogen, you have a +1 charge, and now this become 109 degree because with no more lone pairs available, you just have 4 bonding pair and 0 lone pair. So this is tetrahedral geometry. So 2 is definitely correct there. How about if I check number 1, you have BF3, another AS level case study. So BF3 is a trigonal planar, 120 degree. So if you think about it, it's like this, F and F, this is in 3-dimensional. So this is empty, so something with a lone pair can attack it, and what essentially happened is something with a lone pair can attack it because the boron has 2, 4, 6 electrons in the outer shell. So what you could do is, for example, if you have F minus, then you could have BFF, Now it become 109 degree with a negative charge because now you have 4 bond pair and 0 lone pair. Tetrahedral geometry again, so 1 is also correct. I should have probably moved it onto a new part of a page so that I wouldn't run out of space at all. So there you go, and I'll just put this up again. Let's go through option 3. Option 3 is a CH3 plus. This is called a carbocation. Carbocation is an intermediate for SN1 reaction, nucleophilic substitution. But this is not a tertiary carbocation, it's just a CH3 carbocation. Again, it has a plus on the carbon. Carbon has 4 outer shell electrons, it uses 3 for bonding. It has a plus 1 because you only have 3 electrons in the outer shell. So you have 2, 4, 6 electrons. You're still short of 2 electrons. So what happens is the lone pair can come in and attack that, and you can get carbon, hydrogen, 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 and then you can get a nucleophile like this with a negative charge. Not really a negative charge because you started out with a positive charge there, -1 +1, carbon from 4 bonds with no charge at all. So again, it can accept a pair of electrons. So 1, 2, and 3 are correct. They can accept a pair of electrons. So we're looking at option A as the correct answer. Question 35. This looks tricky. So what do we have? We have X mole of Al2CO6. So Al2CO6 dissolved in water. What do we get? We get the aluminium H2O, 6 and 3 plus. And of course the Cl minus become a free chloride. So I've got 2 aluminium there, so I should have 2 aluminium there. I have 6 times 2, 12 water, so 12 water. What else? I have 6 Cl, so I should have 6 Cl minus like this. Alright, so that equation is done. The second reaction, to precipitate all the aluminium as the hydroxide. So I take the aluminium cation dissolved in water, which is that with the hexa aqua complex. Then I react it with NaOH. I get 3 NaOH, and then I will get so I dissolve to get the precipitate. So the precipitate is aluminium hydroxide. You learn this from your year or IGCSE or O-level qualitative analysis table, which also is something you're supposed to know in your theory paper, even back then as well as now in your AS level as well as A-level chemistry, because you don't get that table of qualitative analysis results in any other theory paper. So the 3 hydroxide goes there to give you this precipitate in this classic precipitation reaction. So what I'll get is I'll get Na. So this thing comes with Cl minus, 3 of them. I can get 3 NaCl, and of course I can get 6 H2O as well. So this is the classic white precipitate that you get to test for Al3 plus with sodium hydroxide. Of course, in excess sodium hydroxide, you can get this complex where, you know, if I add more NaOH, then I'll get AlOH4. This is going to be a minus, and this is going to be a plus. This white precipitate dissolve to give you this colorless solution. So this question is mostly about algebra. So let's see what's going on. If we have, what do we have? So if we have X mole here, so X mole of Al2CO6, X equal to 1. If I have 1 mole of these, then I have Y mole of sodium hydroxide is required to precipitate all the aluminium, all the aluminium. So I have 2 there. So because I have 2 there, so I should put a 2 there, all the aluminium. If I have 2 there, this 3 becomes 6, that becomes 2, that becomes 6, that becomes 12, because all the aluminium goes there. All right. Now, if I produce 2 AlOH3, then this will be 2, this will be 2, and this will be 2. Just to get the whole idea correct, all of this goes here to give you this, all of this goes here to give you this. All right. So let's look at option 2. If X is equal to 1, so if I have X mole of these, How many mole of sodium hydroxide do I need? I need 6 mole. 6 mole. Provided that this is 1 and that give you 2 and this is 2 from here, that requires 6 mole of it. Alright, so let's check option 2. Option 2 say y equal to 3x. We got y is equal to 6 above and x equal to 1 above. Balance equation. Therefore, option 2 is wrong. If option 2 is wrong, there can only be one correct answer, which is only D is correct. Only 1 is correct by logic. Okay, and therefore your only answer here must be D. Question 36, what do we have in question 36? We get nitrogen dioxide gas is produced when petrol is burned in car engine. So you want to know, as a result of the release of nitrogen dioxide into the air, so NO2 released into the air, what would you get? NO2 can react with SO2. This is sulfur plus 4, this is nitrogen plus 4. The SO2 can go to SO3. So there's sulfur plus 6. So this thing get oxidized by an oxidizing agent. And oxidizing agent itself get reduced to give you NO, which is like this. This is a classic equation, alright? And the NO can be regenerated, the NO2 can be regenerated by oxidizing the NO in the presence of oxygen. So which acids are made in the atmosphere? As a result of the release of nitrogen dioxide into the atmosphere, we can get SO3 there. So the SO3 from step 1. So you don't get vanadium 5 oxide catalyst because this is in the atmosphere. This is not man-made. This is in the upper atmosphere where this thing is acting as a catalyst, because you can regenerate it at the end of the reaction. It's not used up. It simply catalyzes the formation of SO3 from SO2. The SO3 from that first step can react with the H2O of rainwater. So you have rainwater plus the SO3. You're going to get H2SO4. This is a classic redox reaction. Sulfur plus 6 is an exercise on oxidation number from your IGCSE or O-level chemistry, or even your AS level redox chemistry. So I can see that I can get H2SO4 as one of my acid, and I can also get HNO3 as one of my acid, because when I dissolve NO2 in water, when I dissolve NO2 in water, so what do I get is this is a classic disproportionation reaction. This is nitrogen plus 4. I'll get nitrogen plus 5, which is HNO3. But I also get HNO2. This is nitrogen plus 3. And the hydrogen is plus 1, so it's plus 4. And this equation needs to be balanced with 2 NO2 like that. So you could definitely get H2SO4. You could definitely get HNO3. You could get HNO2, but what you cannot get is this thing does not stay. Therefore, H2SO3, which is sulfur plus 4, does not get produced because all the SO2 get oxidized to SO3 by the oxides of nitrogen. So you can get H2SO4, but not H2SO3. You can get HNO3, you can get HNO2, but HNO2 is not given as one of the option there. So that is option 3, this is option 2. So this thing here does not get produced. There's option 1, so that's incorrect, which means we are left with 2 and 3. 2 and 3 are correct, so that's C. Phew. Okay, question 37, let's move on. Question 37, you want a major product. So key thing is major, and the other key aspect is going to be nucleophilic substitution. When you read question, you should really underline that kind of thing. And if I look at option 2, option 2 says bromoethane, so 1 and 2, plus ammonia in ethanol. And you do it under reduced pressure in order to force through a single substitution. So this is going to be the major product because of this, as well as heat under pressure, heat under reduced pressure. So option 2 is definitely going to give you that this is a ethylamine, so it's a 2-carbon amine, so it's going to give you ethylamine as the major products. If I check number one is going to be nucleophilic substitution, and this is using K plus and Cn minus. This has to be done in ethanol and reflux, and when you do that, you're gonna do a nucleophilic substitution reaction. So this is going to be the major product. And how do you name this compound? This is 1, 2, and 3. So this is named propane, P-R-O, better spell that properly. So this is propane, and then it's got a nitrile functional group. So propane nitrile includes the longest chain carbon, the most important carbon being the nitrile carbon, 1, 2, and 3. Propane nitrile, 3 carbon there. Alright, so 1 is definitely correct as well. So there's a major nucleophilic substitution product. If you have bromoethane and then you react it with NaOH in ethanol, so the key thing there really is it's not NaOH in water, but it's NaOH in ethanol. So this will do elimination of your hydrogen halide. So there is a hydrogen there, and that is what you are eliminating, HBr. So you will get HBr, and your organic product will be CH2 double bond CH2. This is ethene, which is a gas at room temperature and pressure. So what do you want? They want a nucleophilic substitution reaction. So elimination is not SN reaction. If you want SN reaction, then you have to use NaOH aqueous. Then you will get hydrolysis. In essence, the mechanism of which is a nucleophilic substitution. Alright, but the type of reaction is hydrolysis only when you have NaOH in water, which is aqueous conditions, and not in ethanol. So option 3 is wrong. So only option 1 and option 2 is nucleophilic substitution. So therefore, there will be B as the answer. Question 38. What do we have here? We have excess of P. So P is this thing here. So it's got a carboxylic acid, and it's got a OH there. So the carbon with the OH there is bonded to 1, 2, and 3 other carbon. This carbon with the OH is bonded to 1, 2, and 3 carbon. So this is a tertiary alcohol. This is a carboxylic acid. So excess of P reacts with Q in the presence of corn sulfuric acid. So this is most likely esterification. So this must be ester. But the key question is it the alcohol or is it the carboxylic acid that form ester? So we still don't know yet. And then we say that we get effervescence when you add sodium to it. The key thing really is sodium does react with the alcohol group as well as the OH of the carboxylic acid group. So this will be O minus Na plus like that. And then this will be O minus Na plus like that. So there's the carboxylic acid group reacting with the Na. Metal plus acid give you metal salt and hydrogen gas. Metal plus alcohol give you the alkoxide and also hydrogen gas. By right, you get half mole of hydrogen for every hydroxyl, but you got 2 hydroxyl group that can form the H2, and therefore you get 1 mole of H2. In order to balance the equation, you get 1 of these, and you get 2 sodium. In fact, you need to add 2 sodium in order to balance the equation, and you get that, and you get 2 of the hydrogen giving 1 mole of hydrogen molecule. So this is your effervescence, because that is your gas that you can test with a lighter splint, and it will extinguish with a pop sound as the hydrogen reacts with oxygen to form water. So and that is because this is not the product, so be careful. It is R. If I read the question again, so I nearly got tricked again. So R is the ester. It is the ester that you react with sodium and you get effervescence. Okay, so R is the ester that reacts with the sodium to give you effervescence. So whether this one has formed ester or whether this one has formed ester, you must still have hydroxyl group, still has OH group to react with sodium. So this is not what they want actually. So let's go through the options. So if I go through option 2 first, If this is that, so this is the alcohol, it will react to the carboxylic acid end. So that will give me the original alcohol remains there, and then I'll get an ester, which is a 2-carbon ester, like this. So this thing here, this come from here. Okay, so with that ester, which organic compound could be compound Q? So this ester still has hydroxyl. Hydroxyl is the OH group, so you know NA reaction can do. So 2 is possible. If I look at option 1, I have a carboxylic acid, is ethanoic acid because 2-carbon acid, it will react and form ester in the presence of consulfuric acid as a catalyst, and it will form ester with the tertiary alcohol bit, while this carboxylic acid will remain there. So the carboxylic acid will remain carboxylic acid, and this thing here will form ester. So as you could see there, this thing here, it comes from the ethanoic acid, which is this 2-carbon ethanoic acid. So ester has OH, well, I mean this ester has OH, so reaction with sodium is fine. So 1 and 2 so far is correct. Then if you look at number 3, you have this thing called propanol. Propanol is a ketone, and a ketone does not form ester. Ketone does not form ester, whether you are with alcohol or whether you are with carboxylic acid. So you know it doesn't react to form R. No R is formed, no R ester is formed. So because you don't form R, then there's no product R. So you know, then how can you, I mean, this thing on its own will not react with this, so you still have this that will react with sodium. But since there's no product R, that means this thing cannot be the answer there. So only 1 and 2 are correct, so we're looking at option B being the correct answer there. Question 39. Question 39 is carbonyl compounds. So you have carbonyl, meaning C double bond O, ketones and aldehyde topic, C3H6O. They want something called different observation. So it has to give you different chemistry. If we look at C3H6O, you can have propanol or you can have propanol. So this is propanol, this is propanol. So if I just divide it like this, and then let me just get started. So if I just quickly go through option 1, because you know I could have gone through option 2 first. Perhaps I should go through option 2 first, you know, just to be consistent. So I have Fehling's reagent. Remember, Fehling's reagent contains the blue color solution, copper 2 plus aqueous. This is blue solution. So it will react with propanol and it will not react with propanol. I will get a brick red PPT. This brick red PPT is a result of redox reaction, and I get this thing called copper 1 oxide. Copper 1 oxide is Cu plus 1, so you need 2 of the Cu plus 1 to combine with the O2 minus to give you the brick red PPT. So that gives you different reactions because ketone does not get oxidized by Fehling's, ketones do not get oxidized by Tollens. Okay, so this is a strong oxidizing agent. So because you have aldehyde can be oxidized by that, and you will get purple to colorless. You will see purple to colorless, or very pale pink as the oxidizing agent get reduced when you oxidize the aldehyde, and again no reaction with the ketone. As the ketone there, if you look carefully, the carbon with the carbonyl there has no hydrogen. If you have no hydrogen, then you can't lose hydrogen on that carbon. If there's no loss of hydrogen, then you cannot oxidize it further. Last but not least, so we're looking at number 3. This is alkaline aqueous iodine. In the AS syllabus, this is basically a test for CH3CHOH as part of alcohol topic, and also more importantly is a test for methyl ketone. This is methyl ketone, which we have for propanol. We have the CH3C double bond O, but we do not have CH3CO there, so we have a positive test there, but we have a negative test there. So again, it's differing observations. So all 3 tests will give us differing observations. So option A is the correct answer there. Okay, So what we'll see here is we'll see a yellow precipitate, and this yellow precipitate is what you call triiodormethane, because it's got 1 carbon methane and it's got 3 iodine with 1 hydrogen. So last but not least, question 40, so marking the end of this paper 1, which is fairly long at the moment. Anyway, so we have organic compound T, and then it say does not fizz. Does not fizz means no effervescence. No effervescence means no bubbles. No bubbles means no gases. And this is with Na2CO3. So this is carbonate. Carbonate test for carbonate is by adding acid, and then you will get effervescence of CO2 that will turn lime water milky. So the fact that it said does not fizz and no effervescence with carbonate, so T is not acid. T is not acid. And having said that, you can see option 3 is a carboxylic acid. Just from the name itself is a carboxylic acid, and therefore I can cross out option 3. And if number 3 is wrong, there can only be one answer. Therefore, actually there can be 2 answers, because it could be only 1 is correct or 1 and 2 are correct. So do not jump to conclusion yet, which I nearly did. So let me just double check that. So if I check for number 1, number 1 is propanel. Propanel is an aldehyde, so it's a C3H 1, 2, 3, 4, 5, and 6. So C3H6O. The MR based on the periodic table, so 12.0 times 3 plus 1.0 times 6 plus 16.0 times 1, you can get 58.0. And option 2, you have ethyl butanoate. So I'm going to draw the ester first, and they say it's ethyl, so it's 2 carbon, ethyl 2 carbon, butanoate, so 4 carbon, including this carboxylic acid carbon. So 1, 2, 3, 4. So 1, 2, 3, 4, that will give you the butanoate, which comes from the butanoic acid. So this MR is got carbon, 4 carbon and 2 carbon give you 6 carbon. In terms of the hydrogen, skeletal formula, carbon from 4 bond, so you only show the carbon bonded to carbon or carbon bonded to oxygen. You don't show the carbon bonded to hydrogen. So here you only see 1 bond because there's 3 hydrogen, 1, 2, 3, 4, 5, 6, 7, no hydrogen, 7 hydrogens, 8, 9, 10, 11, 12. So there are 12 hydrogen altogether, and there's 2 oxygen, and you could do the same with the periodic table and get 116.0. So they say compound T, one of the information given in the question is T has 27.6% by mass of oxygen. This is a year 9 O level or IGCSE level chemistry. It's found in the stoichiometry concept. So you need to work out how many oxygen there are in each of these. So if I change the color, so the percentage by mass of oxygen, I have 1 oxygen, so 1 times 16.0 divided by the molecular mass, and I multiply that by 100%, and what do I get? I get 27.6%, which satisfy this thing here. How about the other one? So the molecular formula is different, but if I look at percentage by mass of oxygen, what I have is I have 6 oxygen, so 6 times 16.0 divided by 116.0 times 100%. Put it into your calculator, and I get 27.59%, and that rounded up to 27.6% again. So that is 27.6% by mass of oxygen, as shown to be the percentage by mass of oxygen for compound T. So that makes sense there. And both of these do not contain carboxylic acid, and therefore they will not react with sodium carbonate. They will not fizz with sodium carbonate. So be careful with reading the question. And number 3 there was previously wrong because it contained acid, and it will react with sodium carbonate to give you carbon dioxide. So 1 and 2 are correct. So therefore there's option B there. Alright, so I hope you enjoyed the tutorial on my channel. I've tried to remain true to what I've done even when I was showing the full question paper, but I would assume that you would have access to the question paper anyway if you are doing a Cambridge International A-Levels. I can't tell you where to find the question papers because sharing any links or telling you how to do that, there will be a breach of copyright. I'm just assuming you're a Cambridge learner and you're probably clever enough to find out that on your own. So going forward, my tutorials, I will try to think out loud like this. It appears a bit awkward and I really don't know how long I've spent on this tutorial so far. It's probably quite long, and that is probably because the March 21 papers are actually much more challenging in my personal opinion compared to the other Cambridge International papers I've tried previously. I certainly think that this paper one is a really good paper with a range of questions that actually try to assess a large bit of the curriculum, the syllabus, the specification, which candidates should be able to do by the end of that 1 year spent on AS. Alright, so thank you for watching, and click the button on the bottom right to subscribe to the channel. Follow me at ptet.chemistry, ptet.chemistry on Facebook, Instagram, Twitter, and yeah, let me know how you think this can improve, and let me know in the comment sections as well on whether you find this kind of thing useful or not. Alright, so I look forward to hearing from you and see you in the next tutorial video. Thank you for watching.